Hey guys, today we're going to learn how to evaluate limits algebraically. So what we learned before was how to look at a graph and be able to identify that limit. So today we're going to see how it is that we can find the limit if we're just given an equation. So first, let's see how we can determine that first method of solving limits algebraically. We have this function, and for this first one, I'm giving you the graph so that we can verify our answers and see if we can develop some type of relationship. So we have the function f of x is equal to x squared plus x over x squared plus 4x plus 3. Let's go ahead and factor that function so we can simplify it. So in the numerator, we can factor out an x, and we're left with x plus 1. In the denominator, we can factor that to be x plus 3, x plus 1. And now we can cancel the x plus 1, leaving me with a simplified rational function of x over x plus 3. Now, let's see what happens if I were to take these numbers and plug them in. So first, that's what this says. Find f of a using the equation. And here we have three values of a. So first, we're going to go ahead and plug in that negative 3. So we get negative 3 over negative 3 plus 3, which leaves me with negative 3 over 0. Now we know that we can never have 0 in the denominator, so that means that that value, f of negative 3, is undefined. Now let's look at the graph. If I want to find the limit as x is approaching negative 3, if I look here on my graph, now remember this is a general limit. There is no one-sided here where it's not looking at the negative or the positive. We have a vertical asymptote at x is equal to negative 3. Therefore, the limit is not approaching a real number. Therefore, this limit does not exist. And it does not exist because we have an asymptote. Now let's see what we get when a is equal to negative 1. If I'm looking for f of negative 1, I'm going to plug it in. We get negative 1 over negative 1 plus 3, which leaves me with the answer negative 1 over 2. Now let's see if we can determine the limit at a is equal to negative 1. So here's negative 1. I look down. Remember, I have a hole, but the left side does equal to the right side, and it looks to be about negative 1/2. Now let's go to 0. If I plug in 0, I get 0 over 0 plus 3, which leaves me with 0 over 3. And 0 divided by anything is just equal to 0. Now if I try to find that limit from the graph, if I look at x is equal to 0, the left side and the right side are both approaching the number 0. So that leaves me with this question. When a function is defined and continuous, so remember that here it's undefined, so not at that particular value, at a value of x is equal to a, how can we determine the limit as x is approaching a of f of x analytically? Analytically just means using the equation. So if I look here, if I plugged in that a value, I was able to get the same as the limit value. So as long as the function is continuous at that particular number, we can find the limit by plugging in. That leaves me with the first method. The first method of evaluating limits is using the substitution method, meaning we're going to plug in whatever value x is approaching. So let's try that out. Here we have the limit as x is approaching 0 of 2x plus 1 over x plus 2. So I'm going to plug in x is equal to 0. I get 2 times 0 plus 1 over 0 plus 2, which leaves me with 1 over 2. So this limit is equal to 1/2. Now let's plug in pi over 4 for this limit. So we have 2 cosine of pi over 4. Now remember, for this we're going to need to use the unit circle. And if you look at your unit circle, the cosine of pi over 4 is square root of 2 over 2. So this is going to equal to 2 times the square root of 2 over 2, which my 2's here would cancel, and I'm left with my final answer of the square root of 2. Last one here, we have the limit as x is approaching 2 from the left. Now, even if we're looking at one-sided limits, still just plug in the number and see what happens. Make sure that you get a real number. If you don't get a real number, then that means we're going to have to try another method. So let's plug in the 2. We get the square root of 2 plus 7 minus 3 all over 2. 2 plus 7 is the square root of 9 minus 3 over 2. The square root of 9 is 3, so we get 3 minus 3 over 2, which equals to 0 over 2, which, as we know, equals to 0. So that's basically the substitution method. Just plug in. Now, this should always be the first method that you try because it's the simplest one. And if it works, excellent. If it doesn't work, then we'll use another method. Let's try a couple more. We have the limit as x is approaching 3 from the right of x plus 4 over x minus 1. Again, I'm going to plug in the number and see if I get an answer. 3 plus 4 over 3 minus 1, which leaves me with 7 over 2. That would be my answer. Now let's plug in pi over 3 for this second limit. So we have 2 sine of 4 times pi over 3. So this is my angle. So my angle is now 4 pi over 3. Here I look at the unit circle. As a reminder, the cosine is the x value and the sine is the y value. So if you're looking at your unit circle, you would get that 2 and then sine of pi over 3 is negative square root of 3 over 2. My 2's here would cancel, and I'm left with my final answer of negative square root of 3. Last one here. We have the limit as x is approaching 2 of this function. Let's go ahead and plug in the 2. We get negative 2 minus 1 over 2 times 2 plus 3. Negative 2 minus 1 is negative 3. 2 times 2 is 4 plus 3 is 7. So this is my limit. So that's the first method. Now let's look at what happens if we try to evaluate for a limit with direct substitution and it doesn't work. So let's see. Here I'm given this function. I'm going to go ahead and plug in negative 3 and see if it works. So we have negative 3 squared plus 2 times negative 3 minus 3 over negative 3 squared plus 5 times negative 3 plus 6. Negative 3 squared is 9. 2 times negative 3 is negative 6 minus 3. Over here in the denominator, negative 3 squared is 9 plus 5 times negative 3, which is negative 15, plus 6. 9 minus 6 is 3, minus 3, 0. Over 9 minus 15 is negative 6, plus 6, we get 0. Now here when you have 0 over 0, this is called indeterminate. It's almost like saying undefined, but we're not exactly sure because we end up with 0 over 0. Could be something else happening there. So we just state that this particular limit is undeterminate. Now let's try this one, the limit as x is approaching negative 2. We're going to plug this in, so negative 2 squared plus 2 times negative 2 minus 3 over negative 2 squared plus 5 times negative 2 plus 6. Let's work this out. Negative 2 squared is 4 plus 2 times negative 2 is negative 4 minus 3 over negative 2 squared is 4. 5 times negative 2 is negative 10 plus 6. Now here we get 4 minus 4, which is 0, minus 3 is negative 3, over 4 minus 10 is negative 6, plus 6 is 0. When you have that 0 in the denominator but a different number in the numerator, this means it's undefined. And I cannot figure out what the limit might be. So let's see what is our next method. Now, just because I was not able to find the limit analytically using direct substitution does not mean that I cannot find the limit in some other way. Before we get into that second method, let's look at the graph so you can see what these limits are actually equal to. The limit as x is approaching negative 3, if you look here on the graph, here's negative 3, we have this value here, which even though it's covered by my notes here, if you see these lines are going by 2, so that limit is actually equal to 4. So that's why I ended up with indeterminate, right? When we had that 0 over 0 at x, as x is approaching negative 3, and that's because we had a hole there. Didn't necessarily mean that I couldn't find that limit. Now, if you look at these two, these are both one-sided limits for when x is approaching negative 2. And that's because I have a vertical asymptote there. That's where we ended up where the limit was undefined, or it does not exist, because we had that 0. But if I look at the one-sided limits, I can find an answer. The limit for this function as x is approaching negative 2 from the left, we see that the graph is going up forever, so it would be infinity. Now if I'm approaching x's negative 2 from the right, we have that the function is going down, so that means that this limit is equal to negative infinity. So that leads me to the next method. If I didn't have the graph, I would still be able to find these limits if I were to factor, which is what we did in the very first slide. So we're dealing with the same exact function here, the same one as in the previous two slides. So first we're going to go ahead and simplify this rational function. So in the numerator we have that x squared plus 2x minus 3, which can be factored to be x plus 3, x minus 1. In the denominator, we have x squared plus 5x plus 6, which can be factored to be x plus 3 and x plus 2. I can cancel the x plus 3's, and I'm left with x minus 1 over x plus 2. Notice how my factor canceled at the factor x plus 3. That's where you have the hole, which is where we ended up with indeterminate when we plugged in x is equal to negative 3. But now that we got rid of that hole, we can find this limit. The limit as x is approaching negative 3, now instead of plugging it into the original function, we're going to plug it in to the simplified rational function. So this would give me negative 3 minus 1 over negative 3 plus 2. Negative 3 minus 1 is equal to negative 4 over negative 1, which it gives me the final answer of 4. And if we compare with the previous slide, we see that that limit is equal to 4. So that's the way that you would find that analytically. Factor your rational function, so that way you can get rid of that problematic factor. Because the whole problem was that we ended up with 0 in the denominator because of the x plus 3. So when you get rid of it, you're able to plug in the number and get an actual answer. Now for this one, this is a one-sided limit, right? That x is approaching negative 2. But even with my simplified rational function, if I plug in negative 2, I still end up with 0 in the denominator. And that's because we have a vertical asymptote at x is equal to negative 2. So what that means is, we saw the graph, right? Here's the negative 2. We have one side could be doing this, and the other side could be doing that. So we know that the answer to this one-sided limit is either negative infinity or positive infinity. We saw the graph, we know what it's going to do, but if you didn't see the graph, you can figure this out by plugging in a number that is slightly left of negative 2. Slightly left because we're approaching from the left side. If this was a plus, then we would plug in a number slightly to the right because it's approaching from the right side. So your answer will be some type of infinity, whether it's positive infinity or negative infinity. By plugging in a number slightly to the left of -2, you don't really care about what the number is. What you're looking for is the sign. So a number that is slightly left to the -2 would be x is equal to, let's say, -2.1. And you always want to go very, very close to the actual number. You don't want to do -3 because your function could be defined, or it could give you some other value that it won't tell you more or less if it's which infinity it is. So we're going to plug in just a decimal point to the left. So if we plug it in, remember, to the simplified rational function, because it'll be easier, it would be -2.1 minus 1 over -2.1 plus 2. All I care about is what the signs are going to be. Because again, I know my answer is going to be infinity because of that vertical asymptote. -2.1 minus 1 is a negative number. And -2.1 plus 2 is another negative number, which leaves me with negative divided by a negative would be positive. So my answer would be positive infinity. And if you want to verify that, let's look at the graph. We're doing -2 from the left, and you see it's going up on the left side. Let's try a couple more using this method. So now when you look at rational functions and you're not sure whether substitution will work or if you should go through the trouble of factoring, what I do is I look at the denominator. If I take this number and I plug it into the denominator, 8 squared is 64. 64 minus 64 would give me 0. That's when I know, okay, maybe I should factor this so that I don't go through the work of plugging everything in and ending up with a limit that does not exist, and then you would have to go through the next method. So that's just a little shortcut on knowing whether you're going to use direct substitution or factoring. So let's factor this function. In the numerator, everything is divisible by 2, so I'm going to factor out a 2 first. And that would give me 2x squared minus 7x minus 8. All over, this is a difference of squares, which can be factored as x plus 8, x minus 8. Now let's finish factoring the numerator. We have that 2 still on the outside. X squared minus 7x minus 8 can be factored as x minus 8, x plus 1. And in the denominator, the x plus 8, x minus 8. And now we cancel this x minus 8, which turns out that's my problematic factor. So now when I get my simplified rational function, I can plug in the 8 and get my final answer. So let's plug in 8, and we get 2 times 8 plus 1, which is 9, over 8 plus 8, which is 16. 2 times 9 is 18, over 16, which this could be simplified by 2, leaving me with 9 over 8 as my final answer. Let's look at this one here. Now, we're going to go ahead and factor. The numerator, x squared plus 6x minus 7, can be factored as x plus 7, x minus 1. Now in the denominator, I notice that everything is divisible by 2x, since they all have at least a 2x in common. So I'm going to factor that out first. And I would get x squared plus 5x minus 14. Now let's finish factoring this. We get x plus 7, x minus 1, all over 2x, and this is factored as x plus 7, x minus 2. I cancel out my x plus 7. Now this is my simplified rational function. We have x minus 1 over 2x times x minus 2. if I look at what my limit is approaching, it says 2 from the right. So if it's a one-sided limit, we need to get an answer. One-sided limits will not be DNE or does not exist. At 2, what we have here is a vertical asymptote. So that means that my answer will be some infinity, whether positive or negative. Because this is approaching 2 from the right, I'm going to plug in 1 decimal point to the right of 2 and just take note of what the sign is. So I'm going to plug in 2.1. So that would be 2.1 minus 1 over 2 times 2.1 times 2.1 minus 2. Now 2.1 minus 1 is a positive number. 2 times 2.1 is positive, and 2.1 minus 2 is also positive. Everything is positive, so that means that my final answer will be positive infinity. Last one here, we have the limit as x is approaching 2. If you look at the denominator, that's why we're going to have to factor, is because this denominator will be 0, and we want to see if we can cancel out that problematic factor. So x squared minus 2x minus 8 can be factored as x minus 4, x plus 2, which unfortunately will not cancel with the x minus 2. This is a general limit now. It's not a one-sided limit. So because this is a general limit, that means that my answer here would be does not exist, since at x is equal to 2, there is a vertical asymptote. So if it's a one-sided limit, you're going to take note of the signs by plugging in a number to the left or to the right of the number, and it'll be some infinity. But if it's a general limit and you still end up with 0 in the denominator, then your answer is does not exist. Moving on to our final method, which is the conjugate method. Now, the only time that you really need to use the conjugate method is when direct substitution does not work and factoring will not work, which is normally because you have a radical in your function. So here you see how we have x is approaching 16. But if I plug in 16, the denominator would be 0. So that means I can't use direct substitution. But if I try to factor, this square root prevents me from factoring. So I have to go use this conjugate method. Now what you're going to do is you're going to multiply both the numerator and the denominator by the conjugate of the radical part of the expression. This is my radical, square root of x minus 4. As a reminder, the conjugate is the same thing, but you switch the middle sign. So the conjugate would be the square root of x plus 4. So I'm going to multiply both the numerator and the denominator, which really, if you think about it, the only thing we're really doing is we're multiplying this by 1, because anything divided by itself is 1. So I'm not changing my function in any way. I'm just changing what it looks like. So now here's a special note. When you're multiplying these functions, you're only going to actually multiply the part that has the conjugates. So this is what I'm going to distribute. But over here where it's not conjugates, you're not going to distribute because you're going to see what's going to happen. So let's multiply those numerators. The square root of x times the square root of x is x. Whenever you're multiplying two square roots and what's inside of the square roots is exactly the same, what happens is the square roots just cancel and you're left with what's inside. Now the square root of x times 4 would be positive 4 square root of x. Now let's multiply the negative 4 times the square root of x is negative 4 square root of x. And finally, negative 4 times 4 is negative 16. Over, remember here, we're not going to actually distribute. This would be x minus 16 times the square root of x plus 4. When you simplify this, these middle terms, if you multiply correctly with the conjugates, will always cancel out. So now my numerator is x minus 16 over x minus 16 times the square root of x plus 4. See, this is why we don't distribute, because when you use this method, that problematic factor will cancel out. And now what we're left with is 1 over the square root of x plus 4. Once you have done this, now you're able to plug in the number that the limit is approaching. So I can plug in that 16. I get 1 over the square root of 16 plus 4, which gives me 1 over 4 plus 4, and our final limit answer is 1 over 8. Now let's look at this next example. I'm going to multiply the conjugate of the square root here. Now I know I'm going to use the conjugate method because if I were to plug in 4 into the radical, I would get 2 times 4, which is 8, plus 1 is 9, and the square root of 9 is 3, which would give me 3 minus 3 and 0 in the denominator. Therefore, let's multiply by the conjugate, which is the square root of 2x plus 1. And remember that we only change the sign of the middle. So even though inside of the radical I have an expression, I do not change this sign. I'm only changing this to plus 3. And then the denominator, we have to do the same thing. 2x plus 1 plus 3. Now remember, if they are not conjugates, like in this numerator, we are not going to distribute. We're going to leave it as is. So we have x minus 4 times the square root of 2x plus 1 plus 3. Now in the denominator, that's where we have the conjugates. That's what I'm going to multiply out. So the square root of 2x plus 1 times the square root of 2x plus 1, since the insides are the same, the radical just goes away, leaving me with 2x plus 1. Now distribute. So 2x, the square root of 2x plus 1 times 3 is a positive 3 square root of 2x plus 1. Negative 3 times the square root is negative 3 square root of 2x plus 1. And then negative 3 times 3 is minus 9. So remember, if you did this correctly, these middle terms here will always cancel out since we have the positive and the negative. Now let's combine like terms here in the denominator, and we get x minus 4 times the square root of 2x plus 1 plus 3 over 2x, and then 1 minus 9 is negative 8. Now what I notice here is that in the denominator, 2x and 8 can both be divisible by 2, so I'm going to factor out the 2. So this is what I end up with. The denominator is 2 times x minus 4. See, now this gets rid of my problematic factor. I can cancel these out. And now my new function here is the square root of 2x plus 1 plus 3 all over 2. Now we can go ahead and plug in the 4. So we have 2 times 4 plus 1 plus 3 all over 2. This is 8 plus 1, which is 9. The square root of 9 is 3 plus 3 over 2, which leaves me with 6 over 2, and 6 divided by 2 gives me a final answer of 3. Now what we're going to do is we're going to practice looking at various other examples and determining what method it is that we're going to use, and then applying that method to find the limit. So in this first one, we have the limit as x is approaching 0 of the square root of 2x plus 16. I always want to try out substitution, right? So if I plug in 0, I would end up with a number. So we're going to use here the substitution method. So we get the square root of 2 times 0 plus 16. 2 times 0 is 0, so we have the square root of 16, which is equal to 4. So this is my limit. Over here, I have the limit as x is approaching -1 of x squared plus 6x plus 5 over x plus 1. Now, if I plug in the -1, I'm only really checking the denominator because if the denominator is 0, that means I'm going to have to factor, which if I plug in -1, I do end up with 0, so I'm going to factor this out. So we're going to use the factoring method. The numerator can be factored to x plus 5, x plus 1. And the denominator is x plus 1, which will cancel out here. So my simplified function is x plus 5. Now we can go ahead and plug in the -1. So I get -1 plus 5, which is also equal to 4. Over here, we have the limit as x is approaching 4 of 4 minus x over 2 minus the square root of x. If I plug in 4 into the denominator, I would get 2 minus the square root of 4, which is 2, and 2 minus 2 would give me 0. So that means that I am going to have to use the conjugate method. Since I have a square root, I won't be able to factor. So I'm going to multiply both the numerator and the denominator by the conjugate of the square root expression, which would be 2 plus the square root of x. Remember, only switching the middle sign there. The numerators are not conjugates, so remember we're not going to distribute. So 4 minus x times 2 plus the square root of x. And now in the denominator, we distribute. 2 times 2 is 4. 2 times the square root of x is 2 square root of x. Negative square root of x times 2 is -2 square root of x. And negative square root of x times positive square root of x would give me minus x, since those square roots would cancel. Again, these middle terms here cancel. So now what I have is 4 minus x times 2 plus the square root of x all over 4 minus x. So these here cancel out. And now what I end up with is 2 plus the square root of x. Now I can go ahead and plug in the 4. So I get 2 plus the square root of 4, which is equal to 2 plus 2, which is equal to 4. So this is my limit. Final one here, we're going to go ahead and see what happens. We have the limit as x is approaching pi over 2 of 3x times the sine of 2x. So when you have trigonometric functions, typically you're going to use the substitution method. So we're going to go ahead and plug in the pi over 2. So 3 times pi over 2 times the sine of 2 times pi over 2. Let's simplify this a little bit. 3 times pi over 2 is 3 pi over 2. And then over here, this 2 with this 2 would cancel. Remember that this is part of the angle. So now I need to figure out what is the sine of pi. If you look at the unit circle, pi is over here, and the coordinate there is -1, 0. Since sine is the y value, the sine of pi is 0. So let's plug that in. We get 3 pi over 2 times the sine of pi, which is 0, and 0 times anything would give me a final answer of 0. Now let's look at some properties of limits. Here we have if the limit as x is approaching a of f of x is equal to L, and the limit as x is approaching a of g of x is equal to m, and c is some constant, find each of the following limits in terms of L, m, and c. So L and m represent some answers, the limit for f of x, and m is the limit for g of x. If we have a limit expression that looks like this, where you have the limit as x is approaching a. Look at how these limits are both approaching a. Then if we have f of x plus g of x, we can separate this to be the limit as x is approaching a of f of x plus the limit as x is approaching a of g of x. And since this is L and this is m, then this is L plus m. Now over here is the same thing, but with subtraction. So if we have the limit as x is approaching a of f of x minus the limit as x is approaching a of g of x, then that would be L minus m. And we can do this with all of our operations. If we have division, then it would be L over m. Now, if you have a limit, but you have some constant that is being multiplied before the limit, then we can multiply that constant with the answer of that limit, which in this case, this is f of x, so c times L. If you have your limit that is raised to some exponent, then that basically means that the answer of that limit could be raised to that exponent. So the limit as x is approaching a of f of x would be L and then raised to the p. Now this is an important one. If you have the limit as x is approaching a of a constant, some number, your answer will be that number, whatever the number is. And this is because a constant, if you think about it graphically, is a horizontal line. So no matter which direction you go, the y value, if this is a, would be that number there. So let's apply these properties using some graphs. We have here the graph of f of x and the graph of g of x, and we're going to answer these questions. So here we have the limit as x is approaching 2 from the right of f of x plus g of x. So first we're going to find the limit as x is approaching 2 of f of x, which here is 2, and it says from the right. So from the right would be negative 2. And then we're going to add the limit as x is approaching 2 from the right of g of x. So I go to g of x, here's 2. This is the right, so 6. And negative 2 plus 6 is 4. Now let's look at this one. We have the limit as x is approaching negative 3 of 2 f of x minus 3 g of x. So remember, when you have a constant, you can just multiply that after you find the limit. If I look on my graph here, for f of x, as x is approaching negative 3, we have a hole here, but remember, it doesn't matter as long as the left approaches the right, and that number is negative 2. Now we continue here, so it's minus 3, and I'm going to multiply that with the limit as x is approaching negative 3 of g of x. So here's g of x. We're going to go to negative 3, which is right here, and that is the value of 1. Here, it may be hard to read, but every 2 lines is 1. So this is 1, 2, this is 3, 4, etc. So here's negative 3. And that value is 1. So 2 times negative 2 is negative 4, minus 3 times 1, which is 3, and negative 4 minus 3 is negative 7. Over here we have the limit as x is approaching negative 6 of negative 2 f of x over g of x. So we have the negative 2. We're going to find the limit of f of x when x is approaching negative 6. Which if I look on my graph here, here's negative 6 and it's 2 lines up, so that is 1. Over the limit as x is approaching negative 6 of g of x, here's negative 6. Remember that even though this is the function value, it's not the limit value. The limit value is 4. So we end up with negative 2 times 1, which is negative 2, over 4. That can be simplified to negative 1/2. Here we have all multiplications, so we just have the 2. The limit as x is approaching 4 of f of x, so here's the 4. Here's the limit value, which is negative 3. Then the limit as x is approaching 4 of g of x, which is 4. So now we multiply everything. 2 times negative 3 is negative 6, times 4 is negative 24. Now we have the limit as x is approaching negative 2 of f of x squared. So remember, we're going to find this limit first, and then we're going to square it. So here's f of x, negative 2, which is negative 5. And then we square it. And negative 5 squared is positive 25. Last one, the limit as x is approaching 2 from the right of the square root of 2g of x. So we're just going to keep it inside of the square root, that's 2. And now we find the limit as x is approaching 2 from the right of g of x, which is the 6. 2 times 6 is 12, so we have the square root of 12. Which, if you wanted to, we can simplify this, right? 12 is when you multiply 4 and 3, and 4 can be broken down to 2 and 2. There's my pair, the 3 would stay inside, so this would be 2 square root of 3. However, any answer will be acceptable. And that's evaluating limits.